Hello, welcome everyone, and I hope so. You guys have enjoyed our previous session that we have just conducted, and you get an idea about what is RAG. And in today's session, we have elaborated the importance or introduction about the retrieval augmented generation. Large language models can have a few challenges when it comes for real-time information and the correct answers. Most probably, or widely, large language model has been trained on the data which is available or made available public. The data that is being used for the training for the large language model, where they get the knowledge, where they get the memory, it's coming from public internet. And 99% of data they has used after the cleansing process is the one that is coming from verified public repositories such as Twitter, forums, document libraries, and much more. GPT or models like ChatGPT 3.5, 3.0 Turbo, Gemini, and Anthropic models, or open source model like Llama or Marshalls. These models do not use data from private repositories since they don't have access. If organization want large language model to answer the questions from their private data or the knowledge that's stored in these private repositories or the latest and finest information which those models don't have it, they have two options. One, they can just quickly go in and try to spend up some money and perform fine-tuning, or other ones is RAG, Retrieval Augmented Generation. RAG can be an external database which have all the knowledge in store, or it's become a memory hub for large language model. Whenever you ask any questions from a large language model, first it will retrieve the relevant memory on demand from the database, and then process that with its own learning. You don't need to retrain the model. You can continuously update the database, and it has several of advantages. Some of the important components from the RAG is itself a RAG pipeline, which means that you can convert your existing unstructured or structured data sources into a vector databases in a high dimensional space, so we can apply a cosine similarity, or we can perform a similarity search. We use large language models to convert this normal text into high dimensional space. So once we perform a semantic search, we have the similarity power. So our queries will be converted into the more semantic meanings, and then it's searched in a high dimensional space and only fetch the relevant information. The same process or similar process happens inside the large language model as well. And these models that convert text into vector embeddings called large language models for embedding models. And Microsoft OpenAI have the embedding model available. There are lots of open source models. So what we do, first we extract the data. We try to load the data and extract the text from these PDF or unstructured files, and then we have to split that data, the chunk of data, this big pile of data, into smaller chunks. Imagine that you're trying to basically use one PDF file where the ChatGPT need to parse that in a vector database. The first phase that you load that file in the memory and extract all the text, and then you split that text into the smaller chunks. And a chunking strategy is very, very important. Why, my friends? Number one, chunking strategy will be determine the quality and performance of the query process. Once the query will happen, the relevant chunk will be matched with the user given chunk as well. So that whatever the questions user asks, it will convert into vector embeddings, and it map and search against the chunks that you have stored in the database, but not based on keyword, based on a similarity search, which is much more semantic than and powerful than the generic search. But you could convert a whole book into the embedding model and store them into vector database. But each embedding model have a limitation of a number of token in a single shot, in a single try it can process. In order to overcome this challenge, we break down our text into the smaller chunks and send each chunk to the large language model and convert them into the vector embeddings and store these vector embeddings into our vector indexes, which basically create inside vector stores or vector database. For this particular demo, I'm using embedding model from OpenAI called ADA. I'm using a large language model for furthermore processing for LLM and conversation. It's a GPT-4 or GPT 3.5, and I'm using Microsoft Cosmos DB Mongo vCore or virtual core database. It's a planet scale, complete pass option, and it's a great scalability, highly secure, and greatly available to have a very definite availability options available database. And it's one of the best product that Microsoft produced when it comes for non-SQL databases. It's Microsoft superstar when it comes for store any kind of semi-structured or unstructured data. Now it supports vector database with a MongoDB, vCore, or Postgres. So it's a great option to store your vector data inside or using for your vector store, and it's highly scalable. And this particular component should be the heart and soul of your whole process. There are two major components technically that you need to think it and you need to plan it very carefully when you want to create a scalable enterprise grade RAG process for your LLM or generative AI application. One, the large language model itself for the embedding, and which we are picking the ADA, which is one of the most performant in a high dimensional database that can create on a very high dimensionality, and your database itself where it can receive use for the query and storage. However, Cosmos DB can do a better job in this particular segment. So the process for the pipeline is simple. We get the PDF, we extract the text, perform an ETL out there, extract the text out of it, and then split the text into smaller chunks, send each chunk one by one to the embedding model, and then the returns of the chunk are the vector embeddings, and we upload them into database. That means database is ready. User will going to ask questions, and the fastest questions go for the embedding model again and convert that question in the natural language into the vector numbers. So like vectors are the arrays of numbers, and convert that vector embeddings, and we send that vector embedding for vector search. Also sometimes we call similarity search. System uses a neural network behind the scenes to perform the search out there, its advanced mechanisms, and it used this particular search and return the relevant document only that required for this question. And if it finds, so it find the documents in a high dimension space and match them, and then it return the results. Here we reconstruct our question again. We put our original questions as a user question, and we inject the relevant information that we have extracted on demand from the store and pass this thing in a newly constructed prompt to large language model. Now large language model have all the relevant information that come out of the search and the question that asked by the user, and its own power of summarizing and generating content. Based on that, it generates a response and an answer that will be basically sent back to the user application. And for the furthermore conversation and for history management, they can also keep the chat history that can also help a large language model to furthermore answer the questions or provide the relevant information based on a context that what we're trying to really look into it. Let me show you one example or live demo with the code that what we can do with this product. If we quickly go here, this is my PDF document, and in this PDF document you can see that this PDF document is available here that's called Investment Banking Introduction. It's in a private document that's not available on internet. That means when the ChatGPT was trying to train their large language model, they do not have their hands on this particular book, and they don't have knowledge about that. And how I'm sure about it, let me show you. When you go for the GPT, and here if I'm going to ask a question, you can see that I already have asked question from a copilot, what was the revenue for JP Morgan Chase in 2012, so that it answers me as $99.9 billion, because it retrieved that information from internet and also injected in a same method. Also, GPT have this information by default, but the information that coming from internet. So if I ask a plain GPT, if I make a plain GPT call, a plain prompt without RAG, it's going to return me information something like that, like $99.9 billion, which is incorrect. Why? Because based on my internal document, this document, the JP Morgan Chase has made $91.7 billion of revenue. And when I ask question, I want GPT to perform in the same fashion and then return me the result that is coming from my repositories. Think of this particular information from your databases that you already have the information where their GPT don't have information about your databases. So it can pull the information from your database in order to correctly answer that. So just before I begin that, I'll show you a little bit of the application infrastructure that I have created for the demo. So I'm using Microsoft Cosmos DB for this particular demo, and I'm using Microsoft Cosmos DB flavor called MongoDB. MongoDB Virtual Core is the product that I'm using for today's demo. And you can see here, this is my database that I created, MongoDB vCore, and I'm currently using it M3 tier with the 2 cores and 8 gigabytes of RAM. And it do not have any much functions. If you guys really like to know about how to create and configure a Cosmos DB, I will create another video and share with my teams that will be shared with the appropriate channels. Another product that I'm using from Azure, it's basically called Microsoft OpenAI. Microsoft OpenAI is available, Azure OpenAI. Azure OpenAI is one of the places where you can obtain the models that built by OpenAI, and that's how you can acquire them. And here I have created my resource in East US, and that's my OpenAI Studio. So this is Azure OpenAI Studio 1.1. The new edition is already available in form of AI Studio. I have these models available for me by Microsoft, so I request Microsoft for enable these models for me so I can use them in my production and in my deployments. For this particular demo, I have deployed 2 models, and you can deploy these models very easily by clicking here on deployment, select the model and what are available to you. And if the model is not available to you, you have to look for documentation or request Microsoft to enable it for you. And then put the deployment name, and then you hit create, you're good to go. And if I come up here, and here I have the GPT-4, and here I have GPT-2. These are the 2 conversational models or dialogue models. These models are used for language tasks, for text generation, for summarization, and any kind of conversational bot you want to create. These are the 2 models that you can use it. If you notice that I have another model that called Text Embedding ADA 002 model. This model is designed for performing vector embedding. So I will use the 2 models. One we're going to use here the GPT-4 for the text conversation or text generation, and one for the cosine similarity and vector embedding. So these are the 2 products that I'm going to use. The rest of them is just from Python code. Now we quickly go back to my code pipeline here. Here I'm installing few important libraries for my demo. I'm installing the OpenAI library here. I'm installing Cosmos DB library here. I'm using open source py Python PDF library. Why I'm using Python library? I'm using a Python library at this moment. I'm using a Python library at this moment. If you can see that. And I'm also using at this moment the LangChain library. So in this particular video, which we are basically is producing for you guys, and you're going to get an access over all this code. You will see the step-by-step demo, and also I will make this code available to you. And here, if you can see here, I'm importing my libraries. So here I'm importing some basic common libraries for my code. I'm importing exception from Azure and Azure credentials. I'm importing OpenAI model, and I'm importing OpenAI Azure model, because OpenAI available in 2 different forms. All OpenAI models are available on openai.com on their own service, which you can subscribe and get a subscription and define a connection. And for that, you have to use the same library but different client, different model you have to load from the library. If you're using Azure, you should be using Azure OpenAI model, especially if you're planning to use library 1.1 onward. Now, I import these libraries here. Here I'm putting LangChain, and from LangChain I'm using a couple of models. One, I'm using a text splitter model that helped me to define my chunking strategy, and another one that I'm using is online PDF loader from PDF loader. It helped me to basically load all the text from PDF and then make it available in memory. Then I will use this text with this particular model of a LangChain, which is AI orchestrator, and it convert them them into the smaller chunks. Once the smaller chunking is done, I can pass each chunk to the large language model in order to process it further. You can use the different libraries and different techniques to basically perform chunking. I try to make it simpler and easier that everybody can use with open source libraries. Here I'm going to test the library, and you can see that I'm using the version 1.133 version for OpenAI, which is the latest addition for OpenAI libraries. At this point, I am technically just loading some configuration, connection string for Cosmos DB and password information, and also endpoint information, or like an endpoint address, and also the keys for the OpenAI that required for authentication from my config file. Now here at this point, I decided to load a PFY loader and load the whole PDF file in memory. And once I click here, now I have this PDF file loader is here, and here I'm defining my chunking strategy. You have to make sure that your chunk will be enough big that it can cover the relevant piece of information that will be required later on for search. If the smaller piece of chunk is divided, unoverlapped out there, they could reduce or they could have an impact on the performance of a query and all over the RAG as well. Means you could not able to find the relevant information for your questions. You have to really define your chunking strategy. You have to think the size of the text piece that you needed, and it makes sense when it goes separately or not, or it will be required sometimes separately than each other as well. So you define a chunking strategy. I say that 600 character and the no overlapping. So it will divide the whole text into the pieces, and each piece will be 600 character long. So here I'm loading my data. So when I'm just using loader, load it, this function return the all pass data from this text file, this PDF file, and then I pass this data here into text splitter function as a split document, and that's the splitter I have created, which means that it will going to split this whole text by 600, and whatever the results it will going to show me. I will do it here. So I have this particular PDF file which is almost 16 page long, and it convert this whole PDF file which have tables and text and all sort of things into 82 pieces. It just break down the whole PDF file into 82 pieces. And if I run one of the piece in order to just showcase you, you can see that is the one information. It's the one information that came out of the piece here. So you can see the document content, and here is the metadata as well, that where this piece is coming from. You can see the piece number 1, page number 1, and that's basically the location of the file and little more metadata that it may require. After that, we create an OpenAI client, and this client we're going to use for two major purposes. Number one, we're going to use this client to make a call for large language model for embedding, and also we're going to call another large language model for text processing, such as task generation or answering question. So let's create our embedding. So let's call our embedding model. So I'm creating my helper function here, and it's this helper function I'm calling my large language model deployment name, and here I will provide the text that I want to convert them into vector embeddings. So I'm creating a function where I'm basically getting the one input as text, and that text input will send as a parameter in the function. I'm calling this client. This client is basically coming from here. I have initiated here the OpenAI client. And this OpenAI client, I'm calling a function called embedding, create embeddings, passing that what model I have to use and what text I want to convert. And it returns the data, which I'm going to parse from 0.embedding. And here I'm putting a sleep here. The reason that I'm putting this threading here, doing this thread sleep here, large language models in Azure, especially Azure OpenAI models, have a throttle limits out there. The rate per limit out there, so rate token limits out there, number of token that can be processed in a minute. It's limit by the API size and the configurations. So there are things of 4,000 to 15,000 tokens that you can process per minute. At this moment, that's a limitation. So if I process the data so fast, if I send them a very large request on a very continuous and very fast basis, I might encounter an error that I reached the limit. If I put a 2 milliseconds request here sleep, it will give me enough space and increase the time that it will not reach the limit here. Let's call this function. We initiate this function here. And now I have already all my documents splitted in this particular object as an array, and I'm just passing the first array and passing the one single document here. I'm just testing this function here. So I just send the content to the vector embeddings, and vector embeddings being created and return me the results. And here the results in this particular object. If I print that object, you can see that the numeric representation of the text is already been converted and make it available. So it makes sure, it just make us sure, or just exhibit this thing that our large language model is working fine for embedding, and our embedding function works fine. Now second phase is this, that convert all the text pieces into vector embedding. So I'm creating here the list and one array list here, and here I'm iterating each object from this document, and one by one I'm pulling the one each document from this splitted text out here. Now you can remember that I have 84 documents or chunks, 84 chunks. From here, from these chunks, I will iterate each chunk every single time with my for loop, and try to extract the information, the content, the splitted piece of the text, and send them to that embedded model and wait for the returns. And once I passed it, it send me the vector embeddings. Now I'm creating a new object where I'm adding the original content along with the vector embeddings, and here I just define the name of the field, that content vector. In this field I will save the vector for the content, and in this field I will save the original content. So I will search through this and use that result in order to pass back to large language model. This will have the original plain simple readable information, and this information will be just used for search purposes. When this object is created, I will add them in a list, and I try to store all of them here. Let's try to run them one by one. It may take a few seconds because it has 82 documents to process, and each document have a 2 milliseconds of delay that I have put it. And one in each time they send a request and they convert them in vector embeddings, create a new object, and store them in the list. In a few seconds, most probably 30 to 40 seconds, this process will get completed. However, you can do a parallelization and different technique to optimize this piece based on the amount of data that you want to process. Now let's test that is the vector embedding is done. You can see that one object, in a top one object, I can see the content, and the vector embeddings are already created and stored in this object. Now now we have a vector embedding and the vector content. We can now store this vector content into Cosmos DB. So let's establish a connection. I'm using a MongoDB client here, and I just find the connection string. And here I am defining my database setup. So I'm defining the name, example database, call the collection. The collections are the tables. Consider them as tables in a relational database. So investment collection, and here I just say that if the collection does exist, delete them and add them new. You can see that investment collection is created. It means the table for investment is created. I can load my vector in this table. Here I'm dropping the index and the database if it already exists. I want to make sure that I will create a new one. If you're running my code, if you want to run this code, this will be make it available through GitHub. So don't run this piece of code when you're running first time. Only second time you're running it, you should run that. If you run it first time, you get an error because both database will not exist, neither index. Since I run this demo earlier as well, so I have this database and this index already available, that's why I have to delete them. Now I created a command line here, that way I can just basically configure my search capability and my index capability. Here I'm creating my vector index and defining that which particular column we have to designate for the vector information, where vector information is stored, where the search can perform. So I say this column can be used for Cosmos search, for vector indexing here, for the vector search. And this is the column which contain the vectors. So if search have to perform, it should be in this column. And here is the type vector, and here is the similarity method. So we say cosine similarity that we use here. And here is the dimensions, that how many dimensions the data can be saved, the maximum dimension limits out there. It depends on what large language model you use to create vector embeddings. ADA is basically provide you very high dimensional space of 1536. It's a very high dimensional space, which means that so much relevancy between other words and the content can be saved and stored. It use the method of approximate nearest neighbor approach in in cosine similarity to provide you much more relevant vector results. Now we create this particular command. When you run this command, it creates a vector index. After that, my vector index is ready. Now what I can do, I can load my vector index. This is a list that I have created, and here I'm calling function called insert many. It basically use all this JSON objects that have contained vector and the normal data and upload them into a collection. This is a collection that we have created earlier. Now it's uploading data to Cosmos DB. You can see that in a split of seconds, all these object has been sent to Cosmos DB, and index was earlier created, and now we have just updated the index with the new data. Now I have to configure my search function. Here I'm configuring the search function. So I will get the query from the user, that what user is trying to search, and send that query to the large language embedding model. Embedding model use this text and convert them to vector embeddings, and here I have an embedding query. That's called a vector query. Now I have the vector that I can send to Cosmos DB, and Cosmos DB use this vector to match the vector dimension space inside the vector database in a cosine similarity in a high dimensions, and only the relevant content will be returned in a very semantic manners. And I can tell that how many documents I can expect them to give me back. And by default, I set 5, but you can give other numbers as well. And here I have also asked them to send me the similarity scores. So I'll just call this function. So every time when I run this function, it will send me the results from the documents that I have split and stored them in Cosmos DB based on my query. So let's try to do it here. So in this particular function, I'm asking the questions, what was the revenue of a JP Morgan Chase in 2012? And it will going to send to the Cosmos DB search, and search convert them into vector embedding go and match the relevant documents and return me those chunks back. And in the results, I will find the relevant chunks only from a whole document. Let's plug this. And here you can see that it returns me the 3 different chunks from my database, or 3 different records that have that could potentially have information available for my questions in a very semantic manner. And if you can see here, the JP Morgan Chase information is available here. It defined the table, it defined all that it may contain the revenue information and more, which is fantastic. It basically able to pull out the information that can be helpful to answer my question, because this is the piece that GPT don't have, and that's what I want to provide. Now I configure a method that how I can put this information along with my question to GPT in order to get the more constructive generative answer from GPT. Here you can see that I am basically using a GPT-4 or GPT 3.5, which is a special method of a chat API where you can define a whole dialogue. You can also define the messages that is basically users asking in your API call. In your API call, you can define the message list, and you define the roles, and this role is a user, and the content will be the prompt or the question that user may ask. In the system, you can define the additional data and the requirement and information that ChatGPT model need to know or have to act or have to control, like a personality of the bot, the persona of the bot, the limitations, the blockage, the controls, how it need to respond, how it need to answer, how it need to process things, or any additional information that you want to provide the bot to keep itself. Okay. Now, so here will be the prompt, and the system prompt by default is you are an intelligent assistant for investment banking. So it will act like an investment banking out there. I can provide them a rules that do not answer about other things, be polite. So you can really play around here. And here will be the plain user question. And all of those messages will be, these JSON blocks will be in this array. What I'm doing here, I'm also passing a same prompt to the vector search and getting the vector result. Whatever the result come back out of search, I will add them as a system prompt, as a part of system prompt. So system prompt have this information along the additional information that came out of search result. The search that basically performed through LLM, search that through perform for similarity search. And all that particular knowledge will be injected here. So I'm just saying role system. So role will be system, and the content is basically the one that I have pulled from database, which is very relevant to my answer. And I add them all here. So once LLM will process this information, it has my question and it has a document. So it's check the document and look the questions and able to generate more relevant answer. Here I'm using a ChatGPT client, the OpenAI client that I have created earlier. I'm using a chat completion API, and here I'm creating my request. In this request, I have to provide my deployment name of the model. I'm using GPT 4.0 model here. and this is my deployment name. If you guys remember that earlier I have showcased you, this is the model that I am currently using it. If we go quickly here, and if I plug this model here, this one here, and if I ask question for this model directly here, and I'll just actually clear the text, clear the chat. Okay, let me clear the text, clear the chat, and also I will use the default empty. Yes, clean. If I ask this model plainly, means if I ask that questions directly from this model out there, that please answer me the question, actually does not provide me this API. Sorry, this one. I use the wrong model. So if I ask this question from this particular GPT model here, and it answers me that $97 billion approximately JP Morgan has made it. If I ask multiple times, it might be a style of the answer will be different, but the information will be remain same. But if we take a look back to our module here, it says as 91. So it's a big difference. So this questions, when I ask GPT with this plain knowledge, with this plain information, is this knowledge coming from its training data? This knowledge is coming from a training data. That's I don't want. I want GPT to answer from my document. And I already have configured my prompt here. Let's ask question. The first thing that we're going to ask here, we're going to return this result. I'm going to ask GPT a same question without RAG. This prompt will basically without RAG. Let's run without RAG. An answer will be similar. You can see that it cannot able to answer that because of a guardrails that Microsoft has deployed it. And when I run this same question with the RAG, look at this. Ladies and gentlemen, I'm so proud that GPT able to answer it correctly. Thank you. Thank you for liking it. You can see here that the revenue of a JP Morgan Chase in 2012 is 91.7 billion. And where this information is coming from, even I can use a citation furthermore as well to just reference where this document has pulled 91.7 from the information that we have given, to the large language model, able to use this information to provide us correctly. It's not giving us an information here like this. It's not saying information like this. It is giving us an information based on a data that we have stored privately. So now if you use this particular method, you can provide a latest and updated information for the GPTs, which they don't have, and also give them an access to your own organizational own data sets. So they can talk to your systems, they can call live APIs, and this RAG is not limited to just a process of a historical data. You can also pull information from your real-time applications, other search repositories, from internet to make this process furthermore better. I hope so you like this demo, and it's an end-to-end demo. This code will be made available for you guys. I hope so you enjoyed it, and we have spent really much time to create this fantastic demo. And thank you for being here. If you guys really like to learn more about generative AI, let us know on the Vinces as well, and we host more webinars. And you can also follow us on YouTube and Facebook, LinkedIn, Twitter, and my Twitter accounts and LinkedIn accounts also available, that will be shared by the teams. And thank you for being here. I hope so enjoyed it. Till then, I will hand over to Sweta.